Hello and welcome to The Space Above Us. Episode 84, Space Shuttle Flight 17, STS-51B. Spacelab is go for ops. Last time, we talked about STS-51D. Discovery's fourth flight started off as a routine ComSat deploy mission and ended with some improvised cardboard kludges and the shuttle program's first contingency EVA. The extraordinary steps taken to repair the ailing SYNCOM satellite were ultimately unsuccessful, but once again showed the flexibility and adaptability afforded by flying a human crew in space. Today we'll be talking about STS-51B. The 17th flight of the Space Shuttle and 7th flight of Challenger didn't mark any particular milestone for NASA, but it does for us, and that's because this mission is the 50th flown mission covered by The Space Above Us. Time flies. And apparently, it flies at an altitude greater than 100 kilometers. And we've certainly come a long way since Alan Shepard's short 15-minute flight. This time, we'll be launching a vehicle with more than 60 times as much mass on a mission planned to last almost 700 times longer. We'll also be getting a heck of a lot more science done since this flight represents the first operational flight of Spacelab, Spacelab 3, with the high-tech science facility taking up the majority of the payload bay. If you're wondering what happened to Spacelab 2, it'll fly in a few months. Payload manifests are a mystery. Commanding the flight was former Manned Orbiting Laboratory astronaut Bob Overmyer. We last saw him flying as pilot on STS-5. This is his second and final flight. Flying as pilot was Fred Gregory. Frederick Gregory was born on January 7, 1941, in Washington, D.C. Given his role on the mission, it won't surprise you to learn that Gregory has a classic pilot-astronaut background. U.S. Air Force Academy, helicopter rescue pilot, combat rescue pilot in Vietnam, all that good stuff. He transitioned to fixed-wing aircraft like the T-38 and F-4, graduated from test pilot school, and was working as a research test pilot at NASA Langley when he was selected as an astronaut in 1978. This is his first of 3 flights. Mission Specialist 1 is someone who's had a big influence on the events that we've talked about on the show, but who hasn't come up all that much on his own. Don Lind. We're going to take a special look at his NASA career in a second here, so let's just quickly glance at his pre-NASA life. Lind was born on May 18, 1930 in Midvale, Utah. He earned a bachelor's degree in physics and a PhD in high-energy nuclear physics, with a stint flying jets off of aircraft carriers with the Navy in between. He started working at NASA's Goddard Space Flight Center in 1964, and, well, we'll leave it there for now. Mission Specialist 2 was Norm Thagard, who we last saw on STS-7. This is his second of 5 flights. Mission Specialist 3 was Bill Thornton, who previously flew on STS-8. This is his second and final flight, and while he achieved a lot on his shuttle flights, I'll always remember him for his role in the Skylab Medical Experiment Altitude Test, where he, Bob Crippen, and Bo Bobko spent 56 days in a simulated Skylab to help ensure smooth sailing in orbit. He took it upon himself to exercise all of the equipment as vigorously as possible, resulting in a broken ergometer, some sort of urine centrifuge disaster, and various other destroyed equipment. Thank you, Bill Thornton, for ensuring that the urine centrifuge disaster happened on Earth and not in weightlessness. Joining the main crew were 2 payload specialists. Payload Specialist 1, specializing in material science, was Lodvik Vandenberg. Note that Vandenberg is 3 words and not Vandenberg, the Air Force Base, but maybe they're related, who knows. In any case, Vandenberg was born on March 24, 1932 in Sluiskil in the Netherlands. He earned a master's in chemical engineering and a master's and PhD in applied science. He specialized in crystals, how to grow them, how to grow big ones, how their defects form, and how to use them in various applications. Something tells me his main role on the flight is going to be keeping an eye on the microgravity crystal growing experiments. This is his only flight. And last but not least, Payload Specialist 2, specializing in fluids, Taylor Wang. Taylor Wang was born on June 16, 1940 in Jiangxi, China. He earned a bachelor's degree, master's degree, and PhD, all in physics, all from UCLA. He became a senior scientist at JPL in 1972 where he spearheaded their development effort on containerless processing science and technology research. This is Wang's only flight. As we hit the shuttle era, I've been making an effort to have shorter crew biographies due to the sheer volume of astronauts flying on each mission. But after reading his official oral history interview, I just couldn't resist doing a bit of a deep dive on Mission Specialist 1, Don Lind. This section is going to pull pretty heavily from that oral history, so if you find it interesting, I definitely recommend reading the whole thing. I'll include a link with the episode announcement. Where we left off, Don Lind was working at NASA's Goddard Space Flight Center, studying high-energy particle physics. There are lots of places to study particle physics, but Lind, who had been a big fan of space ever since he was a kid, had an eye on becoming an astronaut, and figured that by doing research at Goddard, it'd be a good way to get his foot in the door at NASA. By the time he arrived at Goddard in 1964, 3 astronaut groups had already been selected. The first 2 required applicants to be test pilots, so Lind didn't qualify. In the third group, the test pilot requirement was dropped, and was replaced with a minimum of 1,000 hours of flying jets. Lind only had 850, but applied anyway, figuring that his PhD was worth the missing 150 hours of flight time. But nope. Various appeals got nowhere, so Lind had to wait. Astronaut Group 4 was the scientist astronauts, which sounds like it'd be perfect, but Lind was 74 days older than the limit. He appealed, saying that since he already knew how to fly, and since it took longer than 74 days to teach new astronauts how to fly, that he should still qualify. But nope. The next year, Astronaut Group 5 was selected, and the age limit had been raised. For the first time, Lind qualified for everything. When he called the astronaut personnel office, the staff, who at this point knew him by name, responded, "Oh yes, Dr. Lind from Goddard. We were wondering how soon you'd call." Third time's the charm, apparently, because in 1966, Don Lind was selected as an astronaut. As a newbie astronaut, Lind couldn't expect to fly for a while, and settled into support roles. One of them was to hammer out human factors and procedures for the crews that landed on the moon, particularly the procedures used during malfunctions. It was especially important that they be dependable since the LEM crews had so much to learn even for an ideal flight that they didn't spend much time training for off-nominal scenarios. Lind played a critical role in Apollo 11 and 12, ensuring that the procedures were well tested and that experiments were simple and quick to deploy. He drove a fair number of engineers crazy by making them strictly adhere to a 10-minute deployment time for all Apollo 11 experiments, sending them back to the drawing board time and time again. Lind likely would have walked on the moon as a lunar module pilot in one of the later Apollo landings, but 18, 19, and 20 were cancelled, and that was that. Lind moved on to Skylab after about 5 years on the job. With Skylab, he continued his work in human factors. His job was to ensure that the crew could actually do what was asked of them and not be fighting the equipment. Want them to change film on a camera? How do they put the camera down? Better add some Velcro. Stuff like that. Lind served as the backup science pilot for Skylab 3 and 4, but that didn't result in a flight since, as he put it, quote, "I was backing up 2 of the most depressingly healthy people you can imagine." Another chance to fly popped up in 1973, when the command module for Skylab 3 began losing thruster quads, potentially necessitating a rescue mission. You can hear more about that one in episode 57. In the end, the rescue wasn't required, and once again, Lind waited for his chance to fly. He almost certainly would have served as science pilot on Skylab B in the mid-70s, but Skylab B was cancelled, and instead of launching it into orbit, they cut a big hole in it and put it in the Air and Space Museum in Washington, D.C. You can still walk through it to this day. 7 years after becoming an astronaut, Lind settled in to wait for the space shuttle. With the shuttle, Lind continued his human factors work. Notable among his contributions was the operation of the remote manipulator system, the shuttle's robot arm. The arm uses different coordinate systems depending on how you're using it or looking at it. The human operator expects different motion based on if they're looking at the arm out the window or looking through the camera mounted on the arm itself. He fought to change hardware in order to prevent a confusing situation where the arm camera would show apparent motion even when everything was still. He had the rotational hand controller tilted to match a natural posture, and he had a bracket added around the translational hand controller to ensure that astronauts had something to grab onto while controlling the arm. The bracket was literally sized to his hand. The shuttle began flying, and for 4 more years, Lind watched from the bench. But at long last, with STS-51B, he was assigned not only a mission specialist seat, but a mission specialist on a science-intensive flight, with Lind essentially serving as payload commander. He missed out on Skylab, but he'd fly with Spacelab. In all, Don Lind waited 19 years and 25 days from his selection as an astronaut to his first flight, the longest of any other astronaut at the time of this recording, and probably for all time. You might imagine Lind as bitter about this long wait, but even when you're not flying, astronaut is a pretty great job. He enjoyed training in various different disciplines with the best instructors the world had to offer. He enjoyed working on science experiments that remain on the lunar surface to this day. And he enjoyed putting his own personal mark on the Apollo, Skylab, and shuttle programs. When asked about the wait, he said, quote, "So even though it was incredibly disappointing not to fly on 2 different missions that I had trained for 10 years, the training and what I was doing while I was getting ready was, to me, absolutely stimulating. Absolutely. It's hard to say whether it was worth it because of the disappointment, but it was certainly a nice way to spend your time. So I had a wonderful experience early in the space program, even though I lost out on 2 flights." Enjoy your flight, Don. You've waited long enough. Before we get to that flight, though, we have a couple of last-minute items to take care of. Among the various crystals and cameras and other science-y things riding in Spacelab for this flight would be 2 squirrel monkeys and a couple dozen rats. Payloads are placed in the orbiter weeks ahead of time, and the entire shuttle stack can sit on the launch pad for quite a while. So with living creatures like monkeys and rats, you can't just pack them whenever you like you can with the other experiments. So here's a problem to solve. You need to get some animals into Spacelab, but Spacelab is in the orbiter, and the orbiter is standing upright on the launch pad. What do you do? What you do is bust out the Module Vertical Access Kit, or MVAC. At the end of the day, this is actually a pretty straightforward device, but something about it just blew my mind. The day before the launch, a couple of technicians drive out to the pad and enter the orbiter in the middeck, ready to head down the tunnel into Spacelab. But since the stack is vertical, that tunnel is now a 40-foot pit. So the technicians start setting up ropes and pulleys and basically go rappelling down the inside of the space shuttle, while carrying monkeys and rats with them. All things considered, it's a nice and easy solution, but I just love that somewhere out there in this world are people who have gone space shuttle spelunking. With the monkeys and rats secure, it was time for launch. On April 29, 1985, the crew clambered aboard and the countdown approached 0. Around 4 minutes before ignition, there was a computer glitch that resulted in some liquid oxygen vents not behaving as expected, which caused a 2-minute and 18-second hold. But launch controllers soon had it fixed, Challenger was a go for launch, and at 11:02 a.m. and 18 seconds, it roared off the pad. From all appearances, it was a perfectly nominal launch. Afterwards, however, it was discovered that the nagging problem of blow-by had reared its ugly head again. And this was the most extreme case yet, with a primary O-ring completely failing to seal and the secondary O-ring sustaining significant erosion from the hot gases escaping. The damage was severe enough that it prompted an internal memo at Morton Thiokol, the manufacturer of the solid rocket boosters. In it, mechanical engineer Roger Beaujolais expressed his concern over the incident, and insisted on the need for immediate action to correct the field joint design. After the Challenger accident, STS-51B crew members Bob Overmyer and Don Lind spoke with some of the Morton Thiokol engineers about their flight. They were shocked when they were told that had the erosion continued for another third of a second, it would have been their mission that was lost. Later on, we will have plenty to say about the Challenger accident and the warnings and close calls leading up to it, so we'll leave it for later, but I thought it was important to highlight this notable step on the timeline. But moving back to the subject at hand, STS-51B is on orbit. For Flight Day 1, Challenger would be maneuvered through a series of different attitudes to accommodate an experiment creatively named the Very Wide Field Camera. It was important to put the camera through its paces on the first day, since the rest of the flight wouldn't be nearly as flexible when it came to attitude. Also on Flight Day 1 was yet another Space Shuttle first: deployable getaway specials. Again, the getaway specials, properly known as small self-contained payloads, were standardized cylindrical experiment containers that could be easily fitted to the payload bay, allowing researchers, companies, and other institutions to fly experiments in space on the cheap. Up until this point, whatever launched in a getaway special also landed with them, but that would change on this flight with the addition of 2 small payloads, motorized lids for their containers, and springs to push the payloads out. The payloads in question were NewSat and Glomer. Northern Utah Satellite, or NewSat, would study air traffic control radar systems from space, and the Global Low Orbiting Message Relay Satellite would, well, relay messages, I guess. NewSat deployed with no issues, but when it was Glomer's turn, the lid wouldn't open, and it had to come home and wait until a later flight. Bummer for Glomer. After Flight Day 1, Challenger slewed to a gravity gradient stabilized attitude. As we discussed when talking about the Long Duration Exposure Facility in episode 78, a gravity gradient stabilized attitude is one that takes advantage of the fact that different parts of a spacecraft are really in different orbits. As long as you're gentle about it, an orbiting spacecraft left-oriented with its long axis vertical to the local horizon will stay like that. That is, even as it revolves around the planet, the same side will always face the surface. No thrusting or reaction wheels necessary. In this case, Challenger flew with its engines facing the ground, and its right wing facing the direction of flight. By staying in this attitude, the orbiter provided a nice, stable platform for delicate experiments, like the crystal and fluid-oriented experiments we brought on this flight. Perfect. To further stabilize things, the extra sensitive experiments were placed as close as possible to the orbiter's center of mass, where the modest centrifugal force created by the orbiter rotating once per revolution were minimized. The crew split into 2 teams, gold and silver, so that they could work around the clock. Overmeyer, Lind, Thornton, and Wang comprised gold, and Gregory, Thagard, and Vandenberg comprised silver. It's time to enter Spacelab and get to work. In case you've forgotten, Spacelab is the European-built research facility designed to be carried in the back of the space shuttle. It essentially turned the shuttle into its own little space station. It first flew on STS-9 as part of a shakedown mission, with this flight considered its first operational flight. It could be arranged in a few different configurations, with this flight carrying a pressurized laboratory module 13 feet in diameter and 23 feet long. The crew would enter the laboratory by floating down a long tunnel connected to the middeck. The tunnel was necessary so that the nearly 24,000-pound Spacelab didn't throw off the orbiter's center of mass. Spacelab generated a lot of data, so it relied on the Tracking and Data Relay Satellite System, TDRS, to communicate with the ground at 50 megabits per second, which is about the same as a modest cable internet connection these days. The laboratory contained 15 experiments that fell into the categories of material science, life sciences, fluid mechanics, and atmospheric and astronomical observations. We don't have time to go into detail on all of them, so let's pick one from each category. For material science, the Fluid Experiment System took advantage of the shuttle's weightless environment to grow some special crystals bigger and more pure than is possible on Earth. Made out of triglycine sulfate, 2 crystals were carefully monitored as they were slowly grown over the course of the mission. And I mean carefully. They used Schlern imagery, which measures fluid flow, and beamed in a laser to make holographic measurements, so scientists on the ground would know just about everything there was to possibly know about how this crystal was formed. And not only would they learn how the crystals were grown, but the crystals themselves would potentially be useful in room temperature infrared monitors. Neat. For life sciences, the Autogenic feedback training experiment was performed on the crew in the name of learning more about that classic orbital problem, space adaptation syndrome. 4 crew members wore instruments to measure their physiological responses, with 2 working through a number of special biofeedback techniques in an attempt to help with their space sickness. The other 2 would just behave as normal and serve as a control. This data would be useful on its own, but would also serve as a handy baseline for evaluating other techniques in the future. For fluid mechanics, we have the dynamics of rotating and oscillating free drops experiment, performed in the Drop Dynamics module. Incidentally, Drop Dynamics module is my favorite EDM band. This particular experiment was payload specialist Wang's main focus. The Drop Dynamics module would use specially crafted sound waves to manipulate drops in the weightless environment. The DDM had some unspecified difficulties getting started, but Wang was extra motivated to get it working and put in some extra hours to ensure that valuable data was obtained. Why was he so motivated? Because Dr. Wang was the first principal investigator of a science experiment to operate that experiment in space. So he was all in on this experiment. In the end, the DDM successfully manipulated drops of various sizes, viscosities, and materials. It even made a drop within a drop. This research would help with the development of containerless processing, where the compound being worked on never actually touches its container, resulting in extra pure samples. And for atmospheric and astronomical observations, something a little different. Not all space experiments have to be super expensive, super high-tech works of scientific art. Don Lind, apparently this is the Don Lind show today, but I guess he's earned it, wanted to get a better look at the aurora, which was something he had studied in his high-energy physics work, but had yet to be photographed clearly from orbit, other than a few in the far distance. The hope was to get a more detailed view from much closer, even flying through the aurora itself if they got lucky. He'd need a decent video camera, but with a few minor modifications, the TV camera already on the shuttle would do just fine. And he'd need a high-quality stills camera and a telephoto lens, which it turns out the shuttle also had. So the grand total for this actually groundbreaking, actually really useful experiment? $36 for some film. Not bad. Oh, and if you're curious, they successfully flew through the aurora 3 times over the course of the mission. That's a cool item to have on your resume. That's a lot of science getting done, and a lot of work. So it's a good thing that when one crew member suggested that the squirrel monkeys were so well adapted to space that they should try letting one out, he was shot down out of concern that they'd never catch him again. After 111 trips around the world, it was time to come home. They had collected over 31 gigabytes of data and recorded more than 3 million frames of images and video. Not bad for less than a week. Just to keep the crew on their toes, one of the payload bay doors indicated that it was not latched. A quick visual inspection confirmed that it was just instrumentation and the door was actually fine. But just to be safe, some test inputs planned for re-entry were skipped to avoid stressing the big composite doors. Landings at the more demanding shuttle landing facility runway were off the table while the nose gear brakes problem was being fixed. So 7 days, 8 minutes, and 46 seconds after lifting off, Challenger touched down at Edwards Air Force Base. Another mission successfully completed. As I mentioned previously, Spacelab missions would form a large part of the Space Shuttle's legacy, opening the floodgates for microgravity research. And with this mission, the laboratory had proven that it was ready for operations and ready for more experiments. It may surprise you to learn that after waiting 19 years, this was Don Lind's only flight. While flying in orbit was a dream come true, he had always intended to return to academia after his stint as a spaceman. And that's exactly what he did, just a little later than expected. Well, did he at least have fun up there? Quote, "Yes, thoroughly enjoyed it. Yes, yes, yes. No, it was a wonderful experience." Next time, we're back on Discovery with a mission that makes it sound like I'm straying out of spaceflight history and into science fiction. That's because, I kid you not, we will be discussing a royal family and Star Wars. Ad Astra. Catch you on the next pass.